Record. Okay. And did I? Now I'm second guessing myself. Okay. Sharing my screen. That's good. All right. I accidentally gave you the weekend off. I meant to post an assignment, so I'll post that today on inference for one sample proportion, specifically hypothesis testing. So I'll post that for you to work on. And now today we're going to start chapter 6. Now I'm going to pull a fast one and skip 6.1 because it's really just review of 5.2 and 5.3, which we spent a lot of time on. And so here, you can review on your own. The only thing we didn't talk about yet is the sample size calculation. And so I'll just kind of hover there. And what I'm going to do is on test 2, I'll put a sample size calculation on there as a bonus question. Okay? Ah, that's nice. So just gotta figure out how to do it on your own. Oh my gosh. You can do it. Then you'll have that bonus. Okay. And so this is the one sample proportion type of question, right? We're going to classify all the questions as a type of question, especially when we're talking about confidence intervals and hypothesis testing. It's going to be really important. And so what we've talked about so far, I'm going to call one sample proportion. This is sections, we introduced it in sections 5.2 and 5.3. And we spent quite a bit of time there, and so that's why we can't afford to spend another day here. But we get to introduce another question type. Finally, a new question type. I know you've been waiting for this. So I'm just going to annoyingly scroll through these slides, and what it does is it introduces a survey question, kind of think about how you would answer it. And then what they've done is, okay, I've included the answer there. Here are the survey results of who answered what, and then we can talk about the proportion of people who answered the second answer, for example, right? That's, I have one sample, and I have a proportion of people who said 500 get the drug, 500 don't. Now, you haven't read the problem yet, so I'll leave that up to you. And then it goes through and it talks about, how do I solve this? How do I make a confidence interval? Well, we already know how, so that's why we're skipping it. Hypothesis test. This might be good just to practice a hypothesis testing question, right? And so, hey, that's not it. Still a confidence interval. Well, fine. Helps if you read it, I guess. Blah, blah, blah. All the answers are in here. And so here, this will be a bonus question on test 2. I promise. We've talked about it briefly, right? We talked about, okay, if I have a confidence interval, then the plus minus chunk is my margin of error. What if I want to force some margin of error before I even collect data? There's kind of 2 scenarios that we're dealing with that the slides will walk you through, right? And so what if you want to cut down the margin of error to 1%, so 0.01? Then you have to unravel what the sample size or the n should be. And on your formula sheet, that's why I feel okay putting it on test 2 as a bonus, because it is on here on your formula sheet. At the very bottom, it's a sample size calculation. All right, come on. All right, so here you're solving for n, a couple of rules. I'll post a little video that I have on calculating the sample size in case it helps. but you know what Z star is. M is the margin of error. So in this case, M is 0.01. And then P star, Q star, that's where the bonus part comes in. You have to figure out what those are. There's two scenarios. Spoiler alert. Okay, so here, blah, 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 blah. I know I shouldn't. Here's a hypothesis test. Practice, practice, practice. Oy, 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 oy. Here, today, we're jumping right into 6.2. Yeah? So 6.2 introduces the second type of problem that we're going to have, which I'm going to call two sample proportions. So the type is two sample proportions. Now, just the general layout is I'm going to have information from two samples, right? Let's talk about college students and UBCO students. That's kind of a group 1, group 2 scenario, right? And so now I might have a proportion of students taking science classes at the college versus a proportion of students taking science at UBCO. Sure, fine. We've got these two proportions. If I want to compare these two proportions, just intuitively, what would you do? You would probably look at the difference between these two proportions, right? Take proportion 1 minus proportion 2, right? Does it matter which one's which? Not really, right? One makes a negative, one makes a positive, but the distance between these two is the same, right? And so that's what we're going to talk about, and that's what we're going to hypothesize about and do inference about, is the difference in these two proportions. So what that's going to look like is we're going to do inference about P1 minus P2. How do these two things compare to each other? Okay. And so usually I'm interested in, hey, are these two different from each other? What do I have to do? I have to assume that they are the same until I have proof otherwise. If they're the same, then the difference is going to be 0, right? And so now I want to hypothesize about how this difference compares to 0. I'm getting ahead of myself, right? But that's where we're headed. And I just want to point out that you would get there on your own, right? Compare these two things. I don't know. How do I summarize the I'm trying to not use difference. I can't. The difference between the two, right? So you have to subtract them, right? And then that's a nice summary of how different they are, okay? And so what I want to do here is just introduce from the formula sheet, okay? Now, it's going to be a little bit overwhelming at first, right? So fun day. We're moving to page 2, the pack page, but there's only 2 pages, so that's nice. And look at all this that we're going to work through today. So if you read a question and you decide, looks like I want to compare 2 proportions, well, then this is the area. Hey, where is it here? On the formula sheet that you're going to be looking at. I can't get the lines. Hey, no. My blank page. Everything is so glitchy today. In my online class just earlier, I was waiting on my iPad to stop lagging when I was sharing my screen. So hopefully that's not, but I'm all plugged in here, so it should be better. But is anyone else having trouble with the internet here today on campus? Yeah, it's a thing. Oh, so annoying. Okay. I'm glad it's not just me, I guess, but still no fun. Make it a little bit smaller. Part of the problem that we're going to be facing now that we have 2 samples instead of just 1 is we're going to have the same information twice over. So I want to summarize that first, and then once we have that all laid out, you'll see that the formula sheet isn't as bad as it looks. Okay, and so let's start with sample 1 and sample 2. Right, we're going to have information from both groups, preferably the same information, right? Otherwise, it's hard to compare them. Let's think about the information that we needed from a 1 sample proportion question. Well, I'm definitely going to need my sample size, which means I need my sample size for group 1, so N1, and my sample size for group 2. Okay. I'm going to have some number of successes in group 1 and some number of successes in group 2, which used to just be X, but now I have 2 groups. And so to keep track of which one's which, X1, X2, fine. Then I needed a P hat. Well, you guessed it, P1 hat and P2 hat. We could even talk about Q hat, which is 1 minus P hat. At this point, you should be familiar with Q hat, right? And I don't usually write it down. I just want to bring it up because it's been a little while. Q1 hat and Q2 hat. That one I don't tend to include. Yeah. So we've got all these components, right? It used to be so easy, and now we're overwhelmed with information. But if we just keep track of sample 1 and sample 2, then let's see here. This, I'll make a note, is not used. It's just theoretical. So you can ignore that. Let's just talk about it though. Right, what it says is that, so we developed the central limit theorem for 1 sample proportion, and what it says is that it still applies for the difference in 2 sample proportions. That's awesome, because if I have a normal distribution, I can use Z to find probabilities, and so that's really nice. That's a nice property to have. It's going to be centered on the difference in the populations, right? Population proportions. And then remember what the standard error used to be? It used to be PQ over N square rooted. Now I have information from 2 groups. So I have P1 Q1 over N1 plus P2 Q2 over N2, then square rooted. It's very, very similar. Problem is, if we had these population proportions, we wouldn't be here. Then we can just look at them and decide if they're different or not. Right? But that's not what we have. And so usually what we're trying to do is either build a confidence interval for the difference in the proportions or do a hypothesis test for the difference in the proportions. Okay. So let's just look at this confidence interval. Looks huge, but if you break it down, right? The point estimate for P1 minus P2, well, my best guess at what this looks like is P1 hat minus P2 hat. Fine. Okay, so just a point estimate again. Plus minus Z star, that's nice. We know how to find Z star. It's the exact same as before. So we use the t-table, the z star line on the t-table, right? We know how to find that. So that's really nice. And then, although kind of clunky, this isn't that bad, right? P1 hat Q1 hat over N1 plus P2 hat Q2 hat over N2, making sure that when you're doing this calculation and then square rooted, you do the first chunk maybe separately, use the store function on your calculator, put that away, calculate the second part, then add them together, and then take the square root. So you're methodical about building it out, right? But then this is the standard error times the critical value. All of a sudden you're back to a margin of error, right? Plus minus some chunk. And now we're building a confidence interval for the difference in the proportions. Neat. Okay. In my mind, I could just let you do it. We're going to do it together, obviously. But knowing where all those components come from and how to plug them in, and you can build this interval, right? Remembering that when you're interpreting the interval, it's about the difference in the proportions. Okay? All right, kind of a broad overview. Now, for our hypothesis test, I'm going to focus on, so I give you two different options for your null hypothesis. Now, the reason is because they're the same, so that's nice. But I want to hypothesize about how P1 compares to P2. And we already got there kind of intuitively, right? If I want to know, is there a difference between them? Well, if there isn't, which is always what I first have to assume, then the difference is 0, right? And so this is the one that I'm going to latch onto. But if P1 minus P2 is equal to 0, what could you do? You could add P2 to both sides, and then you could say, well, that's the same as saying P1 is equal to P2, right? These are equivalent, but just for emphasis about the null hypothesized value is 0, I'm going to focus on this first one, but they're equivalent. So that's neat. Okay. And so this is the null hypothesized difference. Too zoomed in, but that's okay. Okay. Let's pare this down even more. If we just take a step back, Z, that's exciting. We know how Z's behave. Once I have a Z, no matter how I got it, it behaves the same always, right? So I can still find a p-value, and using that p-value, I can still draw my conclusion. And so then once we have this Z in the bag, we're good, right? We can find the p-value, it behaves the same way, we can do our conclusion. It's just getting this Z is a little bit different. I give you two different versions, noticing like I've seen too many times on a test, people do this one and then this one as well, but they're the same, right? All it's done is it's distributed the p hat, q hat over the ends, which to me is more work. And so I'm going to focus, I'm only going to use this one, but if you prefer, you can use this one. That's fine, but I'm going to ignore it. There's a lot of information here. Technically, this is the point estimate. So if we think back to what Z looked like for one sample proportion, we said, okay, it's going to be the point estimate minus the hypothesized value, right? How far is it from the hypothesized value divided by the standard error? And so here, this is how far is it from P1 minus P2? Assuming the null hypothesis is true, well, the null hypothesis is always that P1 minus P2 is equal to 0. So then it's always minus 0. That's why it's not even on the formula sheet, right? Because minus 0 doesn't do anything. So I've eliminated it. It's technically there, but you can just ignore it because you're just seeing how far is this difference in the sample proportions from zero, right? Taking into account the spread. And this is where, okay, we need to spend a little bit of time. Nothing crazy, because notice here that I have a p hat. But Emily, we just said we've got p1 hat, we've got p2 hat, and now all of a sudden there's also a p hat. That's really frustrating when you're first starting out, right? All these p's, p values, everything, right? And so that's why I have this note saying, okay, where p hat is the pooled proportion estimate. Yeah? And there's this really cute, I don't know, comic, I guess, cartoon that I saw in a textbook a long time ago, and I wish I'd kept it because I can't find it now. But it's like this cartoon character pushing all the successes and failures, all the proportions in a pool. And then what it does is if you're a success, regardless of what group you came from, you're in the successes, and then you've got your total. And so what does that look like mathematically? Well, it looks like this. So p hat is the combined number of successes over the combined number of cases. So it's x1 plus x2 over n1 plus n2. Okay? Just an extra step, and I wish we could cut it and just use the same standard error as we did for the confidence interval, but they want me to teach it properly. So, right, this p hat, there's a couple of ways that we can find it depending on the information that you have. But the easiest thing is to, if you have x1 and x2, you can just add them up. And you're going to have n1 and n2, so that's safe, right? The other way that you could find the number of successes in group 1 is n1 times p1 hat. Group 2, n2 times p2 hat, right? Same way that we did before. Okay, besides that, though, I know that's not very nice. Q hat is still 1 minus p hat. So once you have your pooled proportion, then you can find Q hat, and then you've got P hat, Q hat, you've got your N1, your N2, and then you can find your standard error for your Z. Okay, so a little bit of extra work, but nothing too crazy. Well, I guess it's not really fair, is it? For me to say, oh, it's not too crazy. Just briefly, I want to talk about the conditions. They're quite overwhelming, especially for this type of question. And so I'm just going to skim it and highlight the things that you need to keep track of. Okay. And so let's see here. The conditions for two sample proportions, luckily they build off of one sample proportions, but just as before, now I have two samples, so I need to check those conditions twice over, once for each sample, right? And so I use two subgroups for my conditions. I've got the independence condition, and these conditions are outlined later in the slides, but I want to throw them out there so that we can kind of scroll through it relatively quickly later. Get it over with, so to speak. So the independence condition, now this is going to be the same as before, right? I need to have randomly sampled or assume that the sample was randomly selected in order to assume that my observations are independent of each other. Now I have two samples, so of course I need each of them to have independence within the samples, but I also need to have independence between the samples, right? And so that's an additional step, but I'm going to summarize it as randomly sampling or random sampling maybe I'll say not randomly, but random sampling ensures independence within each group, or maybe I should say sample, within each sample and between the samples, between. Okay, so we've got within and between. Now what I want you to remember is the random sampling part and within and between the samples. For completeness, this is one. The optional second one, just for completeness, is the N1 has to be less than 10% of population 1. And of course, N2, has to be more. No, has to be less than 10% of population 2. That one's optional, you can skip that. Huh? All right. These two are going to be the same regardless of if you're doing a confidence interval or hypothesis test, but the normality condition is going to change just like it did for the one sample proportion, which means you're going to have to read through the entire question, right, on the test, and on the final, you'll need to read through the question, figure out what it is you need to do, and then you only check the conditions that apply, right? Otherwise, it's going to take forever. I guess in theory, you could check all of them all the time, but yikes. The normality or the sample size condition, the independence condition is same for hypothesis testing or confidence interval and hypothesis testing. So I think that's how we introduce them. The sample size condition differs for a confidence interval versus a hypothesis test, right? And so what I want to do is I want to outline them side by side so that you can see the differences, and then I'll highlight the differences that you need to remember. So for a confidence interval versus a hypothesis test, here we go. Just as before, with the one sample proportion, what did we need for a confidence interval? We had to have at least 10 observed successes and at least 10 observed failures. Now we have the same scenario, but for each group. That's fine, just more work, right? And so we have to have at least 10 observed successes and 10 observed failures in each group, or in each sample rather. Okay, I'm going to copy this because I'm going to have that on the other side as well with some changes. 10 observed successes and 10 observed failures, right? That's what you need to remember, okay? And of course, the at least is important, but hopefully you'll remember that. So now I'm going to paste this over. The only thing that's changing is the observed is not going to be observed. What was it for the hypothesis test for one sample proportion? Well, we had to have at least 10 expected or hypothesized successes and at least 10 expected or hypothesized failures. Now we have to have at least 10 expected and expected. So I'll highlight that, the difference between the two. How we're going to find the expected is we're going to use the pooled proportion. Use the pooled proportion. Just as a tiny bit of background, right? The null hypothesis is that these two groups are the same. So it shouldn't matter if you push them all into a pool and use the pooled estimate. If they're the same, then that's the hypothesized proportion, right? And so that's the theory. You don't need to remember that. How would we check these things? Let's start with the confidence interval. Well, I've got n1 times p1 hat, which is x1, has to be greater than or equal to 10. I have n1 times q1 hat, which is n1 minus x1, has to be greater than or equal to 10. Notice how I give the scenarios. Just depends on what information you have, right? What's easier. And then n2 times, oops, not q2, not yet. p2 hat, which is x2, has to be greater than or equal to 10. And n2 times q2 hat, which is n2 minus x2, has to be greater than or equal to 10. Just as a reminder, this is sample 1, and this is sample 2. Just have to do it twice over. That's annoying. On the test, I'm not going to make you do that, right? And so you'll just have to check the boxes. But it's nice to know how you would do it. So if we use the pooled proportion, the pool proportion is p hat, which is, I'll throw it on here, x1 plus x2 over n1 plus n2 from the formula sheet. You still have to check both the sample sizes. Are they large enough to detect this hypothesized proportion? They always will be. So you're going to do, but you still have to check it. N1 times P, oh, sorry, not P1 hat, times P hat has to be greater than or equal to 10. N1 times Q hat has to be greater than or equal to 10. N2 times P hat has to be greater than or equal to 10, and N2 times Q hat has to be greater than or equal to 10. Ta-da! What are we checking, just as a reminder? If these conditions are met, which they will be, right, then our sample sizes are large enough to assume that we can draw from a normal distribution. The central limit theorem applies. We're going to use that anyways. Would I ever ask you a problem that you just can't solve because the conditions aren't met? No, that makes no sense, right? So they're always going to be met. It's just a matter of checking to make sure. Okay. No, I don't need an extra page. Okay. So that's a lot, right? Could probably use some some review on your own, but right, just the highlighted parts are the important things to remember in this condition section. So now I want to use an example, right? And so a survey question looks like this. So scientists predict that global warming may have big effects on the polar regions within the next 100 years. One of the possible effects is the northern ice cap may completely melt. Would this bother you a great deal, some, a little, or not at all if it actually happened? So this was a survey question, and the results of that survey from the GSS, it's I think it's the General Social Survey, something like that. It's basically kind of a census from all U.S. adults, not really a sample of U.S. adults, but so the GSS is going to represent U.S. adults. I'm assuming they don't survey children. That'd be weird. It's all kinds of problems with that. So the GSS is this broad survey that goes out to all Americans, and they ask this question, and one of the authors of the textbook teaches at Duke University, so a lot of the examples are around Duke University. How cute, right? And so she did this survey presumably with a group of introductory stats students at Duke University, and here are the results. So now I've got group 1, I've got group 2. Okay, I'm not going to label them group 1 and group 2 because I think even on the next slide she switches and makes Duke group 1 and the GSS group 2. So I'm just going to skip to there. Threw me off earlier when I did this. And so now we've got these survey results. We can talk about that though. So a great deal, hey, some, a little, not at all. Now I'm going to tell you, let's change this to this green instead. Those who answered a great deal, those are the ones that we're going to be interested in our analyses. Okay? You could have picked any one of these lines. What would you do with the remaining lines? Well, those are all failures, right? So you can just say what a success is in your mind. Maybe a success, usually a success is kind of morbid, and so it wouldn't be weird to use the not at all. But for us, let's keep it, light and breezy here. These are successes, right? In this case. So we haven't introduced the problem yet, but those will be considered successes. These are all not a great deal. So we could just zip this up into not a great deal. Not a great deal, which would be a failure in this case. Depends on how you define a success, but here I'm telling you this is what a success is. Okay. So let's see here. Is it on the, not quite the next slide, I guess. In this case, we have the number of successes for the GSS survey is 454. We have the number of successes for Duke is 69. And we have the sample sizes for each of these, right? So we have all these components and we can calculate the sample proportions. Let's see here. Right. What did we need? We needed n, x, and p hat. This will be summarized on a later slide, but I just want to show you where we grab all these things from. I'm going to use G for the GSS and D for Duke. Just to save myself a little bit of writing. NG is the sample size for the GSS, which is 680, and ND is 105. The number of successes, XG is 454, and XD is 69. Oops. 9. Making our P hat G is 454 over 680, and P hat D is 69 over 105. We'll use rounded values. She's rounded to 3 decimal places, and so that's what we'll use. But that's how we would find all those components, right? Even just knowing this, I could ask you find a confidence interval for the difference in proportions, and you could pick away at it and eventually get there, right? That's a nice feeling. Say it so disturbingly. You could pick away at it, spend a ton of time on it. No, maybe not. The parameter of interest that we're actually wanting to talk about, learn about, is the difference between the proportions of all Duke students and all Americans who would be bothered a great deal by the northern ice cap completely melting. And so we're interested in talking about P Duke minus PUS. And so this is where she's swapped the columns very confusingly, to me at least. So that's why I wanted to use these as group 1 and group 2. Right. And so that's why I didn't write it down. The point estimate is the difference between the proportions of sampled Duke students and sampled Americans who would be bothered a great deal by the northern ice cap. So now we have these sample proportions. We've already talked about this, so I'm going to kind of skim through it, right? And so for a confidence interval, we're going to have some point estimate plus minus some margin of error, right? Taking into account our critical value Z star times the standard error. And for the hypothesis test, we're going to calculate a Z, the point estimate minus the null value, how far apart are they, divided by the standard error. And then we find the p-value, and then we're done. Haha. So we just need to figure out what the standard error is. Now we've already seen it, so that's why I'm skipping through it. We've also seen the conditions, but in this case for a confidence interval, right? So this is for a confidence interval. How we would argue independence within groups is the US group is sampled randomly because it's the GSS, and so we assume, or they know what they're doing. And we're assuming that the Duke group represents a random sample as well. Not necessarily the case, but we are assuming it, right? That's a way to get around everything. Say, well, I mean, I assume. That's, no one can fault you for that. And so the sample of Duke students is less than 10% of all Duke students, and 680 is less than 10% of all Americans. That's all fine. The independence between the groups, we're assuming that the sampled Duke students and the US residents are independent of each other. It's reasonable, right? Even if, it's a big if, one of these Duke students was also included in this GSS survey, right? And that's rarely going to happen, right? Even if that's the case, that's only 1 or 2, right? And so it's not going to introduce dependence. And so we assume that these two groups are independent of each other. And then, isn't this so cute? Well, no. Let it, I don't know. She just says, okay, at least 10 observed successes and at least 10 observed failures. Oops. Which is really the takeaway, right? I showed you how to calculate it if you needed to, but as long as you remember that it's the observed successes and failures, then you're good. Okay, so now we're pretending we check the conditions to do a confidence interval. And so what I want to do, instead of using this slide with the answers on it as well, I'm just going to copy this. I'm going to add a page here. And we're going to work through this confidence interval together. A confidence interval is really nice because the question's going to have to say, construct a some percentage confidence interval, right? And so it's going to just push you into it, right? There's no way of misinterpreting that. Harder with a hypothesis test. Usually it says something like, is there evidence that this happened, right? Confidence interval, it just is what it is. Okay, so construct a 95% confidence interval for the difference between the proportions of Duke students and Americans who would be bothered a great deal by the melting of the northern ice cap. Okay, so now I'm going to call this sample 1 and this sample 2. In fact, I'm going to let 1 be Duke and 2 be the US. Making this X1, 454 is X2. I have N minus X1, N minus, or N1 minus X1, N2 minus X2, blah, 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 N1, X, N2, man. And then P1 hat, P2 hat. She's rounded to 3 decimal places. You could try to keep all your decimal places if you wanted, especially using the store function on your calculator. It's easy. One little clue though is usually at the very end, you can round to as many decimal places as you were given in the beginning, right? That's always safe. So in the end, we'll round to 2 decimal places. Okay, so we wanted to make a confidence interval. So here we go. From our formula sheet, I've got Duke students, I've got Americans, 2 groups. I've got proportions from each group telling me this is a 2 sample proportion question, and I want to make a confidence interval. So that's where I'm looking. Bless you. And ta-da, okay. Have all these components, right? Remembering, recall that Z star for a 95% confidence interval is 1.960. That's still the case, right? Roughly 2. You've got the T table, so you can check it, but my iPad's kind of slow, so I'm not going to go there. Okay. P1 hat is 0.657 and P2 hat is 0.668. So from there, we basically have all the information that we need, and we can just plug and chug at this point, right? 0.657 minus 0.668. This is going to yield a negative number, right? Because the second value is larger than the first. If I had swapped the groups, right, then I would get a positive value, but the distance between them is the same, so it doesn't matter as long as you're consistent, right, with your group 1 and group 2. You don't want to be bouncing around, but it doesn't matter, okay? So plus minus 1.960 times the square root of 0.657 times 1 minus 0.657 divided by N1, which is 105, plus 0.668 times 1 minus 0.668 divided by 680, all square rooted. Now I'm gonna Martha Stewart this, I think, because I did the calculation earlier. Okay, I know that's rude. No one minds it when Martha does it though. So I use, in this case, I use the Desmos scientific calculator, which lets me plug in the values line by line and kind of break it up a little bit, right? Because what do we have to be careful with? I have to be careful that maybe I'm gonna, that this, and then I have, right, just kind of doing the calculations individually, storing them, right? The next part here is this, and then the square root, oh, I kind of went lofty there, didn't I? The square root is this value. This is the standard error of P1 hat minus P2 hat. That's my point estimate, right? The standard error of the point estimate. Now I can do cute things like storing it in M, 1.96 times the standard error. Well, this becomes my margin of error. So this whole plus minus thing is still the margin of error. Oops. My point estimate is 0.657 minus 0.668, which is a difference of negative 0.011. This goes, I really used up all my colors, haven't I? This goes here. Those are so similar. Maybe I can find, oh, that one's kind of fun. Let's do that instead. Subtly different blue there. Shows you where it came from. I've got my point estimate. I want to go plus minus my margin of error, right? And so here, this is my point estimate. P is my point estimate. And M is the margin of error. My lower bound of my confidence interval then is negative 0.115, rounding to 3 decimal places. And my upper bound is 0.093. So then I find this interval, right, to 3 decimal places from negative 0.115 up to 0.093. We're going to interpret the interval as soon as I've made an interval, right? That's easy. Well, it's not easy, it's tedious, but it's not hard. I need to interpret the interval. I made a 95% confidence interval, and so we use that same blurb that we memorized last time, right? Because it's always going to apply, right? We use the same blurb always. And so we are 95% confident the interval from negative 0.115 to 0.093 captures now generically the difference in the population proportions, right? But this is where I'm going to snag from the question, right? Construct a 95% confidence interval for, and then this is what I'm going to reword as my answer, right? The difference between the proportions of Duke students and Americans, right? Implying the populations, who would be bothered a great deal, blah, blah, blah. So let me just snag this and put it down here. Put her there. Captures the difference. And you don't need to introduce the proportions there, the population proportions, but you can keep them if you want. The difference between the proportion of Duke students and Americans who would be bothered a great deal by the melting of the northern ice cap. Now, one of the things that I want you to start thinking about is, okay, my hypothesis, my null hypothesis is that P1 minus P2 is equal to 0. I have to assume that there's no difference between them until I have proof otherwise. So let's just think about this, because what we can do is we can use a confidence interval to informally test the hypothesis. It's a nice way to be able to say, to have some sort of guide for when we do our actual hypothesis test of what's reasonable and what's not. So what I want you to think about is, okay, this is the difference in the population proportions. And we've just stated that we're 95% confident that this interval from a negative value to a positive value captures this difference in population proportions. Okay, what does that mean in terms of the null hypothesis then? 0 is in this interval, right? I go from a negative to a positive difference. I'm 95% confident that 0 can be one of the differences in the population proportions. And so it's an informal way of testing the hypotheses, right? And so what you would say is that since 0 is in this interval of the differences, then you don't have enough evidence to reject H naught, right? It's perfectly reasonable, right? From our 95% confidence interval. Sure, there's a 5% chance that we're wrong. Hey, that sounds familiar, right? 5%, 0.05, the alpha level, right? And they're directly related in that way. But that takes time to develop. Okay, and so 0 is in this interval. I've run out of room and I kind of want to keep going, but I did include a question on lab 8, kind of guiding you through how that works, right? Using a hypothesis or a confidence interval to informally test a hypothesis. Okay. Oh, if you've tried lab 8, it's going to be very difficult because we're just introducing that stuff today, right? So maybe hold off until the end of today and then you've got it. Or I guess right now, because that's where it goes to. Okay. It's the curse of having a potential Monday lab and a Tuesday, Thursday class. We're behind. Okay. So here they went through and they did it. She's done a lot of rounding, and so we get slightly different values, but I even use rounded values for the sample proportions. So depending on your rounding, you might get slightly different answers, right? But notice, regardless, it goes from a negative value to a positive value, right? So 0 is within that interval. Oh, maybe I can put it on here. Yeah, that's a good idea. How about I sneak this down here? So now, because I'm on this slide, I'll use this interval instead. That's fine. From negative 0.108 up to 0.086. Well, 0 is somewhere in this interval. Oh, I wanted. Therefore, we do not have enough evidence to reject H naught. Right? There's not a significant difference in the proportions. Okay. All right, here we go. Ready for a hypothesis test? Let's do it. So from here on out, when we introduce a new type of problem, right, because we spent so much time developing what a confidence interval looks like, how we interpret it, how a hypothesis test goes, right? Now, I need to introduce some key things like what's the hypothesis? How do I build a confidence interval? What's my test statistic? Maybe how do I find the p-value if it's a new test statistic, right? But besides that, you can do all these problems, right? If you have those key concepts. So from here on out, I'll give you those key things to start, and then we'll do an example. And then usually that's all I have time for, because I blab so much. There's a lot to say. Okay, so if we want to test if the proportion of all Duke students who would be bothered a great deal by the melting of the northern ice cap differs from the proportion of all Americans who do, then what hypotheses would we be testing? I'm going to use this as an opportunity to highlight things that hypotheses are not about, right? First off, I guess the only one, this one we know is wrong, right? Because it's about the sample. We only hypothesize about the population. The sample, you know everything about your sample. You can calculate anything you want about your sample. So it doesn't make sense to hypothesize, oh, I think they might be different. You can look at them and say, right? And so for that reason, B is out immediately, right? I also want to know if it differs from the proportion of Americans. So that means in my alternative hypothesis, I have to have a not equal to sign, right? And so when I look at these, I've got a not equal to, I've got a not equal to, right? Just rearranged. We've already seen this, so no surprise. But this one has a less than, which is something we might be interested in, right? Is the proportion of Duke students significantly less than Americans, right? We might be interested in that, but in this case, no. Which leaves us with these two options, which are both right, as we've seen on the formula sheet, right? If the proportion of Duke students is the same as the proportion of Americans, well, then the difference between them, the two must be 0, right? And so we could use either one of these. On the test, you're welcome to use whichever one you prefer, right? They're both on the formula sheet. Just pick one that you like and go for it. When I was starting out, I definitely liked this one because then generically P1 equals P2 is always my null hypothesis, right? And then it's easier to compare the two groups. But now I'm moving towards this one just because this is my null hypothesized difference of 0, right? And it highlights that. Okay. The answer is on the next one. Skipping that slide because it's just a recap from one sample proportion. But now, to check the conditions, we need the pooled proportion, right? And so we've already seen it on our formula sheet. And so P hat is the pooled proportion. I jinxed it by saying it wasn't too hot in here, but it's hot in here again. Is there a way to control I asked Steve to turn it down. He's got the class before us in here. Yeah, what's it set to? I mean, it is right there. Thank you. Yeah, just maxing it out. I guess the other morning he came in here to teach and the windows had been left over overnight. So it was freezing in here. You just can't win. Anyways, the pooled proportion is the number of successes in group 1 plus the number of successes in group 2 over N1 plus N2. So we can calculate the pooled proportion because we have the number of successes in each group. And so we have 69 successes in group 1 and 454 in group 2. And we have the total sample size of 785. So 523 over 785. One thing that you can use to check your answer is that the pooled proportion is always going to be between P1 hat and P2 hat. It's going to be pulled towards the larger sample, right? Thinking about the pool, right? But it's always going to be between. So P hat will be between P1 hat and P2 hat. I mentioned that because that's a common mistake that I see, right? Is you get a pooled proportion that doesn't make sense given your P1 hat and P2 hat. So nice to be able to check that. Okay. We didn't check the conditions. Add a page here. And can I be, you know what? I'm not going to add a page. I'm just going to sneak that slide in from before. Where is the conditions? Da, 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 da. Let's see here. Copy. Sneaky. So now, this is the slide from before. Slide from earlier. But I'm going to change it to hypothesis testing. The independence within and between the groups by random sampling for each group stays the same. And for hypothesis testing, it's the expected successes and the expected failures, which you can check by finding N1 times P hat and what was that? N1 105 times 0.666. Well, I'll be lazy and I'll just say it's greater than or equal to 10. I know it is, right? Half of 105-ish. N1 times Q hat is also greater than or equal to 10. N2 times P hat, which is 680 times 0.666. N2 times Q hat. All of these are greater than or equal to 10. Ta-da! You just have to remember the expected versus the observed, right? I'm not going to make you do the calculation on the test, right? I show you because when I post some practice problems that I have, then I do these calculations and I don't want you to be thrown off. But on the test, I'm not going to make you do the calculations. Okay, so instead of doing this with the solutions on the same slide, that seems weird. Then now I'm going to add a page. Well, it's bound to happen. So we've already checked the conditions, right? And now we'll recall, so we've got P hat is 0.666. It's not on there, but throw it on the side. Not as obvious to pick out a hypothesis test, right? Do these data suggest that the proportion of all Duke students who would be bothered a great deal by the melting of the northern ice cap differs from the proportion of all Americans who do? Helpful when it says calculate the test statistic, the p-value, and interpret the conclusion. That's a hypothesis test, right? And so we've already set up and we're the null and alternative hypotheses, but I'll highlight it again here. Okay. And so do these data suggest this, right? Is there evidence of this? That means it's a hypothesis test. So step one, state the hypotheses. We said from our formula sheet, or just looking at the problem, what we want to hypothesize about is whether P1 minus P2 is equal to 0, or if you prefer, P1 equals P2. Now, this is hard to keep track of 1s and 2s. So in your null and alternative hypotheses, I want to see question specific subscripts, or you can say something like, let 1 be Duke and 2 be the US. Especially if I want to know if one's less than the other, it's going to be really hard for me to know if you did it right if you just have 1 and 2, right? And so what I would prefer to see for the hypotheses, I'll say we must, meaning I'll take half a mark off on the test if you don't. Ugh. There's a lot of that. When did she get so mean? For the hypothesis, we must use question-specific subscripts. Oops, subscripts. Which means the null hypothesis is that P Duke minus P US is equal to 0. I'll use D and U, whatever. You don't need to use the question-specific subscripts in the formula because it gets very messy, right? And so you don't have to, but I do need to see it in your null and alternative hypotheses. So here, I'll just do that, right? Which means our alternative, if I want to know if they differ from each other, that's not equal to 0, a difference not equal to 0. And like I said, maybe before, can't remember, what can be confusing if you don't keep your wits about you is we're talking about the difference in proportions being different from 0, right? So you really got to stay on top of those words, right? We're talking about the difference in proportions being different from 0, right? Or significantly different from each other, right? And so now I'm ready to go. I'll make a note to myself that this is going to be a 2-sided test. Because I don't care which extreme, I just want to know if they're different from each other, right? Which is both extremes. I'll add in, we already checked the conditions. So then we're on to step 2. Do the test. Calculate the test statistic. Doesn't have that same ring to it. The test statistic from your formula sheet is a Z. And what we said was, is once I have a Z, then I know what to do with it, right? I know how to find areas in the tail, which are my p-values. And so Z is P1 hat minus P2 hat, my point estimate, technically minus 0, minus P1 minus P2, but my null hypothesis I always assume is true. And so it's not on your formula sheet, but I want you to see it just once. P hat Q hat times 1 over N1 plus 1 over N2. Probably a little bit confusingly, I'm going to just grab the calculation again, that I already did. Sorry, save us a little bit of time here. You don't need to save time, I need to save time. I know. I found my point estimate. I found my P hat, Q hat, and I called it A. I found my 1 over N1 plus 1 over N2, and I called it B, sneakily. My standard error is the square root of A times B, and then Z is P over S. Right? And so I find a Z of negative 0.2224, let's say. So then, and I know I can tell, I need some sort of timer. So I'll use Z is negative 0.2224. Does this jive with what we found for our confidence interval? It does, right? Because they're not very far away from each other, taking into account the spread. So they're not very far from zero, the difference is. And so this tiny Z makes sense. So now find the p-value. I am rushing. How do I set this up? I set up my absolute value of Z equal to negative 0.2224 is going to be between two values on the t-table. Uh-oh. Don't fail me now, iPad. This is one of those cases that kind of confuses people because the absolute value of 0.2 or negative 0.2224 is very, very small, right? In fact, it's somewhere between 0 and 0.674. The one-sided p-value for 0, just the area in one of the tails, is 0.5. The area in both of the tails at 0 is 1. So it doesn't matter. You can have values between these two. So it's somewhere between 0 and 0.674. And that means that we wanted the two-sided p-value, which is going to be somewhere between 0.50 and 1. Now that you have the p-value, you can do your conclusion, but I fear I'm out of time. It's down to the wire. Your conclusion, I'll let you do it on your own, and then we'll pick up there on Thursday. We'll do the conclusion together, but try it and make sure you cover all three parts of the conclusion. All right, and we'll pick up there on Thursday. If you have any questions, let me know. Otherwise, I'll see you then.